Hello, and welcome to video 3 of the chemistry lecture series on topic 1, the introduction to chemistry. Today's topic is significant figures. Significant figures are a very important part of the chemistry and, for that matter, physics as well, as there are a lot of measurements taken in physics and chemistry and sometimes in biology. And as we know from our previous lecture, measurements are not always certain. There's a certain degree of accuracy and precision with all measurements, and as such a system needs to be devised to express those numbers so they are consistent, so they are accurate, and so that we don't get a misrepresentation in our final data. That being said, let's get started. So what are significant figures? The best way to describe significant figures is all the numbers of a measurement that can be expressed with certainty, and the certainty depends on the tool you're using. Some tools are more certain than others, some tools are more precise than others, and some tools are better calibrated. So it just depends on the tool you're using to measure the number of digits that are certain. And then additionally, one estimated number is also significant, because while an estimate's not accurate, it does give a generalized value that can be useful in calculations, because 0.11 centimeters is very different than 0.19 centimeters, and they would come out completely different in calculators, especially if you know with reasonable amount of certainty that it's not 1.9. Also, because of the variety and number of calculations the chemist will perform, a system of certainty has to be used. Otherwise, your numbers just, if you've ever played around with a calculator, they can come out very, very different, even when the numbers are very, very close, especially where decimals are concerned. So we have to have a system in order to make sure our numbers are uniform and can be repeated. So what we have here is a ruler. Now I realize this isn't a real ruler, it's a drawing of a ruler that has pixels and can be construed in numerous different ways, but let's just bear with it and go with the assumption that it's a ruler. This ruler is calibrated to the nearest tenth of a centimeter. That means that we know with certainty the measurements up to a tenth of a centimeter. What we don't know is the measurement between 1/10 and another tenth. So that would be our estimated figure. And I'll do a better job of explaining that here in a few seconds. But let's take a look at this. Okay. If we look at our ruler, we're looking at this blue box right here, which we're going to label as box 1. Okay. If we're looking at our box and we're looking at a ruler, we know with certainty that this box is at least 1 centimeter long. We know that because the edge of this box extends past the 1 centimeter mark. I mean, that's kind of obvious. Most of us have been measuring using rulers since we were in 2nd grade, but I'm just going through the basics here. We also know that with certainty this box extends past 1.1 and 1.2 centimeters. It doesn't quite get to 1.3. So we know that it's at least, which I'm going to draw in blue to indicate our certain digits, our box is at least 1.2 centimeters. Okay, 1.2 centimeters with certainty. We know it extends past 1.2, doesn't quite get to 1.3. That's where our uncertain or our estimated figure comes in. And we call it an estimate because we don't really know where this pixel lines up. We don't really know where this pixel lines up. We don't know where the middle of this line is at because it's not a paper thin line, and realistically no object is at the molecular level. So we estimate that is about halfway between. It's a pretty good estimate, but And since it's a good estimate, we can use it in our calculations. Now, once again, I'm going to use my blue ink for our certain numbers. So we know with certainty that our box is 1.2 centimeters. I'm going to use red to represent our uncertain digit, which is our 5, which represents halfway between the 1.2 and 1.3. Now, if you look at that number, there are 3 numbers there, and that's correct, in that there will be, if you are ever asked how many significant figures are in this measurement, there will be 3 significant figures, or sig figs. Three significant figures in this number, 1.25 centimeters, which is our measurement based on our ruler up here. Now, to further illustrate the levels of uncertainty in different measuring tools, on the screen in front of you, you have 4 different volumetric measuring tools. You have a graduated cylinder on the far left. That's what this tool is. It's graduated cylinder, and it is calibrated to the nearest 1 milliliter. You can tell by looking at this cylinder that the volume in the flask is above the 9 but below the 10. That means with certainty you know that you have 9 milliliters. And you can say, well, with pretty close to 5. So you've got 9.5 milliliters would be the measurement in this volumetric flask, volumetric graduated cylinder, and that would have 1 certain digit and 1 uncertain digit, so for 2 sig figs. On this graduated cylinder, which is calibrated to the nearest 10 milliliters, you can't get that accurate. Now, you can still, with pretty good estimation, say that there are 9 milliliters in this flask, but you can't say anything more. You don't know if it's 9.2, you don't know if it's even 8.5, but you've got a pretty good guess that it's 9, and that's all you can say. So there's only 1 significant figure for this particular measurement. You can say kind of the same thing for these 2 beakers over here, but with even less certainty because the lines abbreviate. They don't wrap all the way around, and beakers are not great for measuring volumes. They give you a good reference number, but not an exact quantitative value. Once again, you can pretty much just say that there's a pretty good estimate that there are 9 milliliters in this one, and possibly I would call this 9.4. And based on our graphic, I think all 4 of these are supposed to have the same value, so that even just in our graphic, you can't tell with certainty what the last digit is, and that's an excellent example to illustrate how measurement and significant figures can be important. Now, obviously, all the numbers we use in chemistry won't come directly from the lab. That's just not practical. So you have to have rules for recognizing which figures are significant, even if you've not taken the measurement yourself. And there are some rules for that, 5 to be exact. The first one is all non-zero numbers are significant, period. If a number is not a 0, it's a significant figure. Now that is before calculation, not after, but before calculation, all non-zero numbers are significant. Zeros that appear between other non-zero digits are also always significant. So like over here, 39,004, these 2 zeros are still significant. Zeros that appear in front of all non-zero digits are called left-in zeros, and left-in zeros are never significant. So right here, 0.000416, there are only 3 sig figs because those first 3 are just placeholders. You can easily convert that into scientific notation and eliminate those 4 zeros, no problems. Zeros that appear after non-zero digits are called right-end zeros, and right-end zeros in a number sometimes are significant, but a lot of times they are not. So in this case, 140, there's only two significant figures. Unless, of course, it is an exact measurement you're getting, you can still convert that to scientific notation and only have two significant figures. And also, if your number ends here, this is also right-end zero, but your decimal place is 0.0, you have to assume that zero is there for a reason. They ended their measurement right on that zero, so that's a significant number, and you need to include that. So that's the difference. If it ends in no decimal point, you can convert that to scientific notation and only have 4 sig figs. Here, you need to take note of that, and that's why those are significant, but these are not. Now, because not all numbers are significant and not all numbers are important, which indicates the significance, you have to have a method for reducing your number to one of the proper sig figs and do so in a regular manner. And that's where rounding comes in. Rounding is an old concept to you. Most people understand it at this level, but I still need to briefly discuss it just in case. First and foremost, rounding is reducing the number of digits expressed in a number in order to indicate the level of certainty of the measurement. The easiest way to describe it is to look at a number. For example, our first number, 26.54, if we round that, we would round it up. And the reason we round it up is it's a 5. Anything 5 or over, you round up. So if our number was only supposed to be 4 significant figures and they've obviously expressed 5, we need to reduce that to 26.55. So we take the digit beforehand and we round it up if it's a 5. In the second one, 159,765.2, and we're only supposed to express 6 sig figs in this case, we would round down because this number, this 2, is under 5. So we would just round to 159,765. Round down means we just leave the number beforehand alone. And finally, this scientific notation number, let's say we are rounding it to 3 significant figures, which a lot of times when you punch in calculators, you'll get these really long numbers and only need 3 sig figs. It's important to note you don't bother this. That has no impact on what numbers are significant. So where you begin your rounding is right here, because 1, 2, 3 is our significant figures. You round to 1, 2, 5, add in your decimal, and then you leave the exponent alone. And that's how you round. As I mentioned beforehand, sometimes you'll have to do calculations with your measurements. It's not just enough to take a measurement. Sometimes you'll have to do some math or some dimensional analysis with your measurement. And there are different rules depending on the types of functions you're using. The addition and subtraction rule is actually rather simple. For functions that include addition and subtraction, you round to the number of decimal places equal to the component number with the smallest number of decimal places. It's a little hard to understand just reading it, so let's go ahead and take a look at an example. In our example, 12.3456 plus 129.56. Both of these numbers have decimal places. One of them has 2, that would be this one right here. The other one has 4. So our component number with the smallest number of decimal places is this one. Even though it's the larger number and it has fewer significant figures, it has the least number of decimal places. So when you add these two numbers together, you will get a value of 141.9 0.056. And since it's an addition problem, we have to round that to the nearest tenth of a place. So we would reduce that to 141.91 would be our final answer there because of the addition and subtraction rule. Unfortunately, the rule is different with multiplication and division, though not really difficult. For functions involving multiplication and division, round to the number of significant digits as the component with the smallest number of significant figures. In this case, in multiplication and division, the number of decimal places is irrelevant. So consider using scientific notation if you've got a large number that has extra zeros. And I'll show you what I mean. Here we have 9.062 times 1,270,000. Lot of zeros there. So we need to figure out just how many significant figures there are. For this one, there are 5. You have 3 non-zero numbers and 2 zeros that are placed between 2 non-zero numbers. So there are 5 significant figures there. Over here you've got 1,270,000. There are only 3 because these right in zeros are placeholders. There are only 3 sig figs there. So when you do your calculation, you get a value of a really large number, 11,437,874. Now that is a very large number, and we have to reduce it to 3 significant figures. The best way to do this is to use scientific notation. So you take your first 4 digits, since you know that you will need 3 sig figs thanks to this number, and you round this 3, which gives you 11.4. That leaves you with 0.00000. In this case, that's 3 significant figures, or if you so choose, you could also represent this as scientific notation, which would be 1.14 times 10 to the 7th power. Either number is acceptable because either number correctly represents the proper number of significant figures, once again, which is 3. So, next time we will cover dimensional analysis, the process of converting one unit of measurement or one value into a completely different unit based on an equivalency. We'll see you next time.